Tonight, we journey into one of the strangest choices in all of astronomy. A measurement unit called the parsec. Almost no star actually exists at this exact distance, yet this unit appears in virtually every professional paper written about the universe. By the time we finish, you will understand not only what a parsec is, but also the remarkable story behind why a measurement decision made back in 1838 continues to shape astronomy even now. If you find these cosmic explorations interesting, a like or subscribe makes a difference. Let us begin. Picture yourself as an astronomer in the year 1837. You spend your nights at the telescope, watching a dim star known as 61 Cygni. You understand that Earth is traveling through space, circling the Sun at incredible velocity. You realize that with enough patience, enough precision, enough care, you might detect the star's position shifting just slightly against the backdrop of more distant stars. And if you can measure that tiny shift, you will achieve something humanity has attempted for 2,000 years. You will measure the distance to a star. Friedrich Wilhelm Bessel accomplished exactly that. What he could not have predicted was that his measurement would establish a distance unit still dominating astronomy almost 200 years later. A unit that seems completely unintuitive to anyone outside the field. A unit that marks no natural boundary anywhere in space. A unit based entirely on the geometry of his measurement method, the parsec. For most of our history, the distances to stars remained a total mystery. The ancient Greek astronomer Hipparchus, working around 130 BCE, catalogued more than 1,000 stars. He measured their positions with care, tracked how they moved across the sky, recorded their brightness levels, but distance? He had absolutely no idea. His best estimate placed them all on a crystal sphere beyond the planets, each one equally far from Earth. This was not ignorance or failure of imagination. It represented the best explanation that fit the observations available at the time. The stars looked like fixed points of light that never shifted relative to one another. They maintained perfect formation night after night, year after year, century after century. The ancient Greeks actually had a specific term for this celestial sphere. They named it the firmament, derived from a Latin word meaning to make firm or to strengthen. The concept suggested that stars were literally embedded within a solid crystalline sphere that rotated around Earth once each day. This sphere existed beyond the planets, which the Greeks knew moved against the stellar backdrop. They had tracked Mars, Jupiter, and Saturn with great attention and observed these wandering stars trace elaborate paths through the constellations. But the stars themselves never budged relative to each other. Aristotle, writing during the 4th century BCE, argued that this celestial sphere must consist of a fifth element, different from the earth, water, air, and fire found below the moon. He called this substance ether, or quintessence. This material was perfect, unchanging, and eternal. The stars embedded within this sphere shared its perfection. They never changed in brightness, never appeared or vanished, never moved except for their daily rotation with the sphere itself. This model made sense for 2,000 years because nobody possessed instruments capable of detecting stellar parallax or proper motion. The stars genuinely appeared absolutely fixed. Every observation seemed to confirm the model. When Ptolemy assembled his great star catalogue around 150 CE, documenting more than 1,000 stars and their positions, he discovered the same patterns Hipparchus had recorded 3 centuries before. The constellations had not changed shape at all. For 2 millennia, nobody managed better. The technology simply did not exist. Telescopes were eventually invented during the 1600s, and they revealed astonishing details about the moon, planets, and stars. Galileo observed mountains on the moon and 4 moons circling Jupiter. He discovered that the Milky Way consisted of countless individual stars, but he still could not answer the fundamental question of how far away these objects actually were. The stars appeared absolutely fixed. If something does not move, you cannot triangulate its distance. You need to observe an object from 2 different positions and measure how its position changes. That is how your brain perceives depth. Your 2 eyes see slightly different views of the world, and your brain uses that difference to judge distance. Close one eye and try to touch something. It becomes harder because you have lost that depth perception. Your brain needs the parallax between your 2 eyes. For stars, we needed something similar, but on a cosmic scale. Human eyes are separated by only about 6 centimeters. That provides enough depth perception for objects a few meters away, but proves utterly useless for anything at astronomical distances. We needed a much larger baseline. By the 1600s, scientists had figured out a clever approach. Use Earth's orbit around the Sun as your triangulation baseline. Johannes Kepler had established that Earth orbits the Sun in a roughly circular path. By the mid-1600s, astronomers had measured Earth's orbital size fairly accurately by observing transits of Venus across the Sun's surface. They understood that Earth orbits in a path about 300 million kilometers in diameter. That equals 186 million miles. This means that in January, Earth sits on one side of the Sun, and 6 months later in July, Earth occupies the complete opposite side. Observe a star in January. Note its exact position against the background of more distant stars. Then observe that same star in July from the opposite side of the orbit. You are viewing from 2 positions separated by that full diameter. It resembles having eyes separated by 300 million kilometers instead of 6 centimeters. Even the nearest stars should display a tiny shift against the more distant background stars. This shift is called stellar parallax. Measure this shift, use basic trigonometry, and you can calculate the distance. The concept is beautifully simple. Draw a triangle. The base represents Earth's orbit diameter. The vertex marks the star. Measure the angle at the star and you can determine how far away it is. Simple geometry that any student learns in school. The execution, however, proved nearly impossible. The problem was that the shift is incredibly tiny. We are discussing angles smaller than 1 arcsecond. To understand how small 1 arcsecond is, imagine dividing a degree into 60 parts. Each part equals 1 arcminute. Now divide each arcminute into 60 more parts. Each of those equals 1 arcsecond. So 1 arcsecond is 1/3600th of a degree. To give you a physical sense of this, if you hold a tennis ball at a distance of 1 kilometer, the ball appears about 1 arcsecond wide. If you are standing on a beach and you see a ship on the horizon 10 kilometers away, a person standing on that ship's deck appears about 1 arcsecond tall. That represents the kind of precision 17th century telescopes would need to detect stellar parallax. They could not do it. The best telescopes of that era had mechanical wobbles larger than the signal astronomers were trying to detect. Atmospheric turbulence blurred images by several arcseconds. Temperature changes made telescope parts expand and contract by amounts that threw off alignment. Even the astronomer's own heartbeat could introduce vibrations large enough to ruin measurements. The foundations of observatory buildings settled and shifted with temperature. Wind pushed on telescope tubes. Robert Hooke tried in 1669. He was a brilliant scientist, one of England's leading experimenters. Hooke had contributed to optics, mechanics, astronomy, and biology. He coined the word cell after observing the structure of cork under a microscope. He formulated Hooke's law of elasticity. He was a serious scientist tackling a serious problem. Hooke built a special telescope mounted in a tall building to minimize atmospheric distortion. The idea was that mounting the telescope high up would place it above some of the turbulent air near the ground. He observed a bright star called Gamma Draconis for months, took careful measurements, detected what he thought was a shift in position. He published his findings, claiming to have measured stellar parallax. Other astronomers could not reproduce his results. The shift Hooke detected was likely instrumental error or atmospheric effects, not genuine parallax. His measurements were not precise enough. The instruments were not stable enough. The attempt failed, but it established a pattern. Over the next 150 years, multiple astronomers would claim to have detected stellar parallax. Each time, further investigation revealed the measurements were wrong. The task proved harder than anyone imagined. James Bradley, working in the 1720s, built better equipment and made more careful observations of Gamma Draconis. He detected a shift in the star's position, but the pattern was wrong for parallax. The star shifted in the wrong direction at the wrong time of year. Bradley had actually discovered a different effect, called stellar aberration, caused by the finite speed of light combining with Earth's motion. This discovery was important for understanding light, but it still did not measure stellar distance. By 1800, astronomers had been searching for stellar parallax for well over a century with no success. This actually told them something important. The complete absence of detected parallax meant the stars must be enormously far away, much farther than most people had guessed. If the nearest stars were reasonably close, someone should have measured their parallax by now. The fact that nobody had succeeded despite increasingly sophisticated attempts suggested distances vastly greater than early estimates. By the 1830s, technology had finally advanced enough to make success possible. Telescopes had improved dramatically. Better glass for lenses, better metal for mounting structures, better mechanical designs for smooth tracking. Astronomers understood atmospheric effects better and knew how to minimize their impact. Measurement techniques had become more refined through decades of attempts and failures. Several astronomers realized that success was now within reach, and they began serious, systematic programs to detect stellar parallax. This created a race. Friedrich Wilhelm Bessel in Germany, Friedrich von Struve in Russia, and Thomas Henderson in South Africa all began independent programs to measure stellar distances using parallax. Bessel had certain advantages. He was methodical, careful, and patient. He had spent years refining astronomical measurement techniques. He understood error analysis better than almost anyone. He chose his target star wisely. Rather than selecting the brightest stars, which are not necessarily the closest, Bessel selected a star with large proper motion. Proper motion means the star's slow drift across the sky over years and decades, measured relative to very distant background stars. Stars with large proper motion are usually nearby. If a star is moving through space at typical stellar speeds, the apparent motion across our sky will be larger for nearby stars than for distant ones. It works the same way cars on a distant highway seem to crawl across your view while a car passing right next to you zooms by quickly. Bessel reasoned that a star with large proper motion was likely to be relatively close, making its parallax larger and easier to detect. He selected 61 Cygni, a faint double star in the constellation Cygnus. This star had the largest proper motion known at the time. Bessel observed it repeatedly over more than a year, comparing its position to nearby background stars that appeared motionless. He used a special instrument called a heliometer, designed to measure small angular separations with high precision. Month after month, he recorded measurements. He corrected for atmospheric refraction. He corrected for the aberration of light. He corrected for instrumental effects. He accounted for every source of error he could identify. And finally, in 1838, he announced success. He had measured the parallax of 61 Cygni. The shift was tiny, only about 1/3 of an arcsecond, but it was real, reproducible, and consistent across multiple observations. Bessel calculated the distance. Using the baseline of Earth's orbit and simple trigonometry, he found that 61 Cygni sits at a distance that light takes more than 10 years to travel. This was the first time anyone had measured the distance to a star. It was a monumental achievement, one of the great milestones in the history of astronomy. For the first time, we knew the scale of interstellar space. Shortly after, Struve measured the parallax of Vega, and Henderson measured the parallax of Alpha Centauri. The race was over, but what mattered more than who finished first was that the technique worked. Humans could now measure distances to nearby stars. The cosmos was opening up to quantitative investigation. The parallax measurements immediately revealed something profound. The stars are unimaginably far away. Even the nearest stars sit at distances that dwarf anything in our solar system. Light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star takes more than 4 years. The distance scales were staggering, almost incomprehensible. Astronomers needed a convenient unit to express these enormous distances. They already had astronomical units for measuring distances within the solar system. One astronomical unit equals the average distance from Earth to the Sun, about 150 million kilometers. That unit works well for planets, but becomes unwieldy for stars. Even the nearest star is more than 250,000 astronomical units away. The numbers become cumbersome. They needed something else, something that reflected how stellar distances were actually measured. And here is where the parsec enters the story. The word parsec is a contraction of parallax arcsecond. It defines distance based directly on parallax measurements. 1 parsec is the distance at which a star would show a parallax of exactly 1 arcsecond. Let me explain this more carefully. Imagine a star sitting at some distance from us. We observe it in January from one side of Earth's orbit, then in July from the opposite side. The baseline between these two observation points equals 2 astronomical units, the diameter of Earth's orbit. The star appears to shift slightly against background stars. That angular shift is the parallax. If the parallax equals exactly 1 arcsecond, then by definition, the star sits at a distance of 1 parsec. If the parallax equals half an arcsecond, the star sits at 2 parsecs. If the parallax equals 1/10 of an arcsecond, the star sits at 10 parsecs. The relationship is simple. Distance in parsecs equals 1 divided by parallax in arcseconds. This definition might seem strange, but it has a beautiful elegance for astronomers actually doing parallax measurements. Measure the parallax angle, invert it, and you immediately get distance in parsecs. No complicated conversions or unit transformations required. The measurement directly yields distance in the natural unit for parallax work. For working astronomers in the mid-1800s, this made perfect sense. They were measuring parallaxes. They needed a distance unit that connected simply to those measurements. The parsec did exactly that. It was elegant, practical, and intuitive for the people using it. But here is the peculiar part. Almost no stars actually sit at exactly 1 parsec distance. The definition is purely conventional, based on a human choice about angular measurements. There is nothing physically special about 1 parsec. No natural phenomenon occurs at that distance. No boundary exists there. It is just the distance corresponding to 1 arcsecond of parallax, and 1 arcsecond itself is arbitrary, a human convention from ancient Babylonian mathematics. Why did the Babylonians divide circles into 360 degrees? Partly because 360 has many divisors, making calculations easier. Partly because their year had roughly 360 days, creating a pleasing correspondence between daily motion of the sun and angular measure. Why divide each degree into 60 minutes and each minute into 60 seconds? Because the Babylonians used a base 60 number system. These were practical choices for ancient mathematicians, not discoveries about the nature of space. Yet these ancient arbitrary choices cascade forward through history. They influenced how we measure angles, how we define parallax measurements, and ultimately how we established a fundamental distance unit in astronomy. The parsec exists because of geometry choices made thousands of years ago in Mesopotamia. 1 parsec equals about 3.26 light years. That is, the distance light travels in 3.26 years. It equals about 30.9 trillion kilometers, or about 19.2 trillion miles. It equals about 206,000 astronomical units. These numbers are useful for context, but the parsec was not defined by reference to any of them. It was defined purely from parallax geometry. The nearest star system to us, Alpha Centauri, sits at about 1.3 parsecs. Sirius, the brightest star in our night sky, sits at about 2.6 parsecs. Betelgeuse, the red supergiant in Orion, sits somewhere around 170 parsecs away, though uncertainty remains about its exact distance. These are the kinds of distances parsecs measure naturally. As astronomy advanced through the late 1800s and into the 20th century, the parsec became increasingly standard. More astronomers used it in their papers, more textbooks taught it, more observatories adopted it as their standard distance unit. But not everyone was happy about this. Some scientists argued strongly for different units. The light year had obvious appeal. It connects distance directly to time, something everyone understands intuitively. Light travels at finite speed, about 300,000 kilometers per second. In 1 year, light covers about 9.5 trillion kilometers. That distance is 1 light year. It is clean, conceptually simple, and relates to a fundamental physical constant, the speed of light. Many popularizers of astronomy preferred light years. They found it easier to explain to general audiences. A star 10 light years away means we see it as it was 10 years ago. Light left that star a decade ago and is just now reaching our eyes. This connects distance to time in a way that helps non-specialists grasp the scale involved. But professional astronomers generally stuck with parsecs. Why? Partly because of historical momentum. By the early 1900s, a substantial body of literature used parsecs. Changing would require converting all existing measurements. It would make older papers harder to use. It would break continuity with established work, partly because of practical convenience. If you are measuring parallaxes directly, parsecs remain the natural unit. Your observations give you angles. Convert those angles to parsecs and you have distances. Converting to light years requires an additional calculation step. For someone doing hundreds or thousands of distance measurements, that extra step is an annoying inefficiency, partly because of professional identity. Using specialized terminology that outsiders find confusing can actually strengthen community bonds among insiders. Astronomers all learn parsecs during their training. Using parsecs signals membership in the professional community. It is part of the shared language that makes you a real astronomer rather than an amateur enthusiast. This pattern appears across many specialized fields. Doctors use medical terminology that confuses patients. Lawyers use legal jargon that confuses clients. Physicists use units like electron volts that confuse non-physicists. Part of this is genuine efficiency in communication among specialists. Part of it is social signaling about expertise and group membership. The parsec situation is complicated further by the existence of related units for different distance scales. For nearby stars, astronomers use parsecs. For more distant objects within our galaxy, they use kiloparsecs, meaning thousands of parsecs. For distances to other galaxies, they use megaparsecs, meaning millions of parsecs. This creates a consistent system spanning many orders of magnitude. Our Milky Way galaxy is about 30 kiloparsecs in diameter. That equals 30,000 parsecs. The distance to the Andromeda galaxy is about 780 kiloparsecs. That equals 780,000 parsecs. The observable universe extends to distances of billions of parsecs, or gigaparsecs. Having consistent prefixes across this enormous range helps astronomers think about different scales using the same basic framework. Light years would work just as well for this purpose. You could use light years, kilolight years, megalight years, but because the astronomical community standardized on parsecs early, that became the system everyone learned and used. Changing now would require coordinating across thousands of astronomers worldwide, updating countless databases and software tools, and rewriting huge amounts of educational material. Is it worth the effort? Most astronomers would say no. The parsec works fine. It is awkward to explain to outsiders, but that is not really a problem for professional research. Papers are written for other astronomers, not for general audiences. Conference talks assume specialized knowledge. Research conversations happen among people who all learn the same system. For these purposes, parsecs function perfectly well. In fact, you can argue that parsecs work better than light years for certain types of calculations. Many important relationships in astronomy involve distances in parsecs directly. Absolute magnitude, the intrinsic brightness of a star, relates to apparent magnitude and distance through a formula that is cleanest when distance is measured in parsecs. If you use light years, you need extra conversion factors cluttering up the equations. The distance modulus, a concept used constantly in observational astronomy, is defined as 5 times the logarithm of distance in parsecs, plus 5. This formula would be messier with light years. Parsecs make the math slightly simpler. Not dramatically so, but enough that working astronomers appreciate the convenience. These kinds of technical details matter when you do calculations every day. If one unit system makes your daily work 5% easier, you will strongly resist changing to a different system, even if the alternative seems more intuitive to outsiders. Scientists are practical people. They use tools that make their work easier, not necessarily tools that seem elegant to non-specialists. There is also an interesting pedagogical argument for parsecs. Learning about parsecs forces students to understand parallax geometry deeply. You cannot grasp what a parsec is without understanding how parallax measurements work. That understanding is valuable. It connects distance measurement to actual observational technique. It makes students think about how we know what we know, rather than just memorizing numbers. Light years, by contrast, are almost too intuitive. Students can understand what a light year is without understanding anything about how astronomical distances are measured. That superficial understanding might actually be less valuable than the deeper geometric thinking required to grasp parsecs. Maybe the difficulty is a feature, not a bug. Still, the parsec remains deeply weird to anyone encountering it for the first time. Why would you define distance based on angular measurement? Why not just use lengths directly, like kilometers or miles? Why not use time, like light travel time? Why connect it to an arbitrary angular convention from ancient Babylonian mathematics? These questions have no satisfying answer except historical accident and path dependence. Parsecs emerged from parallax work. They became standard because the people doing that work found them convenient. They persisted because changing involves costs and coordination problems. There is no deep physical reason the parsec is the right unit. It just happens to be the unit we chose, and we have stuck with it. This is actually typical of measurement systems generally. Most units are arbitrary historical choices, not discoveries about nature. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. That is a completely arbitrary choice. It reflects 18th century French politics more than physical reality. The meter could have been defined as any length. We chose that particular length for practical reasons at that particular time. Similarly, the second was originally defined as 1/86,400th of a day. Why 86,400? Because 24 hours times 60 minutes times 60 seconds equals 86,400. Those subdivisions are Babylonian conventions, not natural divisions of time. We could have divided days into 10 hours of 100 minutes each. Some revolutionaries tried exactly that during the French Revolution. It did not catch on, but there was nothing physically wrong with it. Units are human constructs. We invent them for convenience. Sometimes, different communities invent different units for the same quantities. Then those communities have to either coordinate on a single standard or maintain conversion factors between systems. The history of measurement is full of competing standards, political battles over which system to adopt, and practical compromises between different conventions. The metric system versus imperial units represents one famous example. The metric system is objectively better designed. It has consistent decimal scaling. All units relate through powers of 10. Conversions are simple. The system was designed rationally from scratch to be coherent and easy to use. Imperial units grew organically over centuries. They have inconsistent conversion factors. 12 inches per foot, 3 feet per yard, 1,760 yards per mile. It is a mess. Yet, the United States still uses imperial units for most purposes. Why? Partly because of enormous infrastructure investment. Every road sign, every blueprint, every machine tool, every construction standard uses imperial units. Changing would cost billions of dollars, partly because of cultural identity. Americans associate metric with foreignness. Imperial units feel American. Changing seems like abandoning tradition. These are social and political factors, not scientific ones. They shape outcomes just as strongly as any technical consideration. The same forces keep parsecs dominant in astronomy. Technical quality of the unit matters, but so does installed base, community practice, institutional infrastructure, and social coordination costs. Interestingly, some specialized astronomy subfields have partially moved away from parsecs. Cosmologists working on the largest scales sometimes use megaparsecs or gigaparsecs, but they also frequently use redshift as a distance proxy rather than proper distance measures at all. Redshift measures how much light has been stretched by cosmic expansion. It connects directly to observations and avoids certain conceptual complications about what distance even means in an expanding universe. Planetary scientists working on objects within our solar system use astronomical units almost exclusively, not parsecs. One astronomical unit equals the average Earth-Sun distance. It is the natural scale for planets, asteroids, and comets. Using parsecs for solar system objects would be silly. The nearest object beyond our solar system is more than 200,000 astronomical units away. Within the solar system, parsecs are simply the wrong scale. So astronomy actually uses a patchwork of units depending on context. Astronomical units for solar system work, parsecs for stellar distances, kiloparsecs for galactic scales, megaparsecs for distances between galaxies, redshift for cosmological scales. Each subfield uses whatever unit makes their specific calculations simplest. There is no single universal distance unit across all of astronomy. This is completely pragmatic and reasonable. Different problems call for different tools. A carpenter uses different measuring tools for different tasks. A ruler for small measurements, a tape measure for room dimensions, a surveyor's chain for property boundaries. Using the right tool for the scale you are working at makes perfect sense. Insisting on a single universal tool for all contexts would be impractical. The parsec story also illustrates a deep truth about scientific units and measurements. We think of measurement as discovering pre-existing facts about nature. We imagine that distances are out there in the universe, and we are just finding their values. In some sense, this is true. The distance from Earth to Alpha Centauri has an objective value independent of human observation, but the units we use to express that distance are entirely human constructs. Nature does not care whether we measure in parsecs, light years, kilometers, or any other unit. Those are labels we apply to make numbers manageable and calculations convenient. The physics is the same regardless of units. The choice of units reflects human psychology, history, and social organization more than physical reality. This does not make the units arbitrary in the sense of being useless or interchangeable. Some units really are better than others for particular purposes. Parsecs are genuinely more convenient than light years for parallax calculations. Meters are genuinely more convenient than feet for scientific work because of decimal scaling. These practical advantages matter, but they are advantages for human users, not fundamental features of nature. Recognizing this helps us understand both the power and limitations of scientific knowledge. Science discovers real patterns in nature. Those patterns exist independently of human observation. But the language we use to describe those patterns, the units we use to quantify them, the mathematical frameworks we use to calculate with them, all reflect human choices. Different choices would work, though perhaps less conveniently. This becomes especially clear when we look at how parallax measurements actually work in modern astronomy. Today, astronomers do not physically observe a star from different points in Earth's orbit and measure angular shifts by eye. Instead, sophisticated space-based telescopes like the Gaia mission measure stellar positions with incredible precision over years of continuous observation. Gaia has measured positions and parallaxes for more than 1 billion stars. That is billion with a B. The precision is astonishing, down to micro-arcseconds for bright nearby stars. A micro-arcsecond is 1/1,000,000th of an arcsecond. To give a sense of this scale, a micro-arcsecond is roughly the angle subtended by a human hair viewed from the distance of the moon. With this level of precision, Gaia has revolutionized our understanding of stellar distances within our galaxy. We now have accurate distance measurements for millions of stars. This creates a three-dimensional map of our galactic neighborhood with unprecedented detail. We can see the structure of spiral arms, the distribution of star clusters, the motion of stellar streams, all in quantitative detail, impossible 20 years ago. All of these measurements are reported in parsecs and milliards seconds of parallax. The entire Gaia catalogue uses these units. Software tools for analyzing the data expect these units. Research papers discussing the results use these units. Converting everything to light years would be possible, but would serve no scientific purpose while creating substantial practical inconvenience. This reveals something important about scientific standards. They are partially technical choices about what makes calculations easier, but they are also social agreements about shared conventions. Everyone agrees to use the same units so that data can be easily shared, compared, and combined. The specific choice of units matters less than the coordination on a single standard everyone adopts. This coordination function of standards is crucial for science. Scientific knowledge is cumulative. New research builds on previous results. This only works smoothly if everyone uses compatible methods and reports results in comparable formats. Standards create the common language that makes accumulation possible. Without shared standards, every research group would generate incompatible data that could not be directly compared or combined. The parsec serves this function. It is the shared distance standard for stellar astronomy. Whether it is the best possible standard is beside the point. It is the standard everyone uses, which makes it functional for enabling scientific progress. Changing to a better standard would require coordinating across the entire global astronomy community. Unless benefits clearly outweigh costs, such changes do not happen. We see this pattern throughout science. Fields settle on particular standards, methods, and conventions. These become entrenched through accumulated practice and infrastructure. Changing requires overcoming substantial inertia. This is not necessarily bad. Stability in methods and standards has real value. It lets scientists focus on new discoveries rather than constantly reinventing basic tools. But it does mean that historical choices have lasting consequences. The units, methods, and standards that happen to get established early often persist for decades or centuries, even if alternatives might be objectively better in some ways. Path dependence matters. The route taken to get to current practice shapes what that practice looks like. In the case of parsecs, the path ran through parallax measurements in the 1830s. That measurement technique naturally produced angles. Converting angles to distances required a distance unit defined by angular measurement. The parsec filled that role elegantly. As parallax measurements became more common and more accurate through the late 1800s and 20th century, the parsec became more deeply embedded in astronomical practice. By the time alternative distance measurement methods emerged in the 20th century, parsecs were already standard. When Henrietta Leavitt discovered the period luminosity relationship for Cepheid variable stars, allowing distance measurements to much more distant objects than parallax could reach, those distances were still reported in parsecs. When Edwin Hubble used Cepheids to measure distances to galaxies and discovered the expanding universe, he reported distances in megaparsecs. The unit persisted across technological changes in how distances were actually measured. This is common for units. They tend to outlive the original measurement methods that inspired their definition. We still use meters, even though nobody measures distances by reference to the equator anymore. We still use seconds, even though nobody uses sundials to define the length of a day. Units become conventions independent of their original rationale. Today, astronomers measure distances using many different methods depending on distance, scale, and object type. Parallax for nearby stars, main sequence fitting for star clusters, Cepheid variables for nearby galaxies, type Ia supernovae for distant galaxies. Each method has different systematics, uncertainties, and applicable ranges. but they all report distances in parsecs or related units like kiloparsecs and megaparsecs. The unit unifies a patchwork of measurement techniques. This unification function is valuable. It lets astronomers compare distances measured by completely different methods. A distance measured from parallax can be directly compared to a distance measured from Cepheids. The common unit makes comparisons straightforward. If different methods use different units, constant conversion would be required. That would introduce opportunities for error and make comparisons awkward. So the parsec has evolved from a unit defined by a specific measurement technique into a general-purpose distance unit for astronomy. It is no longer tied conceptually to parallax, even though the name suggests that origin. It is simply the standard way astronomers express stellar and galactic distances. This evolution from technique-specific unit to field-wide standard is a typical pattern in scientific measurement. The story of the parsec also illustrates how explanations can be difficult to convey to outsiders, even when the underlying concept is not especially complicated. The mathematical relationship is simple. Distance in parsecs equals 1 divided by parallax in arcseconds. That is a one-line equation. But explaining why this particular relationship defines a useful unit requires explaining parallax, explaining angular measurement, explaining why 1 arcsecond serves as the reference angle, explaining the historical context of parallax measurements. It becomes a long story. This is common in science. Simple mathematical relationships often rest on extensive conceptual infrastructure. The simplicity is apparent only after you understand all the background. To someone encountering the concept fresh, it seems complicated and arbitrary. This creates communication barriers between specialists and non-specialists. Specialists forget how much background knowledge is required to make simple statements make sense. These communication barriers can create public misunderstandings about science. People sometimes conclude that scientists use unnecessarily complicated jargon to exclude outsiders or make themselves seem smarter. Sometimes that accusation has merit, but often the specialized terminology serves genuine functional purposes. It captures subtle distinctions that matter for technical work. It connects to theoretical frameworks in ways that everyday language does not. It enables precise communication among specialists. The challenge is finding ways to explain specialized concepts to non-specialists without sacrificing accuracy. This requires translation, not just simplification. You need to find analogies that work in everyday experience. You need to explain the conceptual motivations behind technical choices. You need to acknowledge what seems strange or arbitrary and explain why those choices were made. This documentary attempts that kind of translation for the parsec. The hope is that by understanding the historical and practical context, the parsec makes more sense, even though it remains somewhat arbitrary. It is arbitrary in the sense that other choices could have worked, but it is not random. It emerged from genuine needs of working astronomers. It solved real problems in a practical way. It persists because changing would be costly and benefits are unclear. These are comprehensible reasons, even if they do not make the unit seem natural. Understanding this story changes how we think about scientific standards and conventions. They are not handed down from nature or discovered as fundamental truths. They are negotiated by communities of practitioners working on particular problems in particular contexts. They reflect pragmatic compromises between competing considerations. They embody historical contingencies and path-dependent processes. They serve social functions of coordination and communication alongside technical functions of enabling calculations. This does not make science arbitrary or unreliable. The patterns science discovers are real features of nature. But the frameworks we use to describe those patterns are human constructions. Different frameworks could work. The framework we actually use reflects our history, our psychology, and our social organization as much as the structure of physical reality. Recognizing this helps us be more sophisticated consumers and practitioners of science. We can appreciate why experts use specialized language without assuming that language is designed to confuse outsiders. We can understand why changing established practices is difficult without assuming that means current practices are optimal. We can see how social factors and technical factors jointly determine scientific practice. The Parsec gives us a concrete example to think about these abstract issues. It is a real unit used in real research with real consequences for how astronomy gets done, yet it is also clearly arbitrary in deep ways. No natural phenomenon occurs at 1 parsec. The definition depends on ancient Babylonian angle conventions. Almost no stars sit at exactly that distance. It makes no intuitive sense to anyone not trained in astronomy, yet it works. It enables precise communication among astronomers. It connects to measurement techniques in useful ways. It scales consistently across enormous ranges of distance. It is embedded in databases, software, textbooks, and professional practice. It serves its purpose well, even if that purpose is not apparent to outsiders. This combination of arbitrariness and functionality characterizes many aspects of scientific practice. Some people find this story disillusioning. They want science to be purely about discovering truth, not about historical contingencies and social conventions. But I think the real story is more interesting. Science is a human endeavor done by humans embedded in cultures with histories. That does not make it less valuable or less reliable. It makes it an amazing collective achievement. Humans created measurement systems from scratch. We invented units, standardized them, coordinated across cultures and centuries to maintain common standards. We built instruments of incredible precision to measure phenomena at scales, from subatomic particles to the entire observable universe. We developed mathematical frameworks to describe patterns at every scale. We established social institutions to train new generations, fund research, review findings, and accumulate knowledge. All of this is human work, human choice, human construction. The parsec is one small piece of this enormous edifice of scientific practice. It is a unit of distance used by professional astronomers. It emerged from practical needs of parallax measurements in the 1830s. It became standard through social processes of coordination and standardization. It persists despite recognized limitations because changing is difficult and benefits are unclear. This makes it a perfect microcosm of how scientific standards actually work. When you read an astronomy paper that reports a distance of 50 parsecs, you are now seeing layers of meaning that were invisible before. You see the measurement technique that originally motivated the unit. You see the geometric relationship between parallax angles and distances. You see the historical contingencies that made this particular unit standard. You see the social processes that maintain standards across global research communities. You see human choices shaping scientific practice in ways that persist for centuries. This kind of insight makes science more human, not less scientific. It shows that science is something we do, not something that simply exists independently of us. We make choices, we establish conventions, we coordinate on standards, we build institutions and infrastructure, we train new practitioners. All of these human activities are essential for science to function. Understanding them gives us a richer appreciation for how science actually works as a social and technical practice. The parsec will probably remain astronomy's standard distance unit for the foreseeable future. The costs of changing are high, the benefits are unclear, the existing system works well enough. Astronomers have more important things to worry about than distance units. They are trying to understand dark matter, dark energy, galaxy formation, stellar evolution, planetary systems, and dozens of other deep questions about the universe. The choice of units is a technical detail that rarely constrains this work, but maybe someday circumstances will change. Maybe some new measurement technique will emerge that makes a different unit more natural. Maybe some international coordination effort will decide that harmonizing units across different fields justifies the transition costs. Maybe some new generation of astronomers will decide that starting fresh with better conventions outweighs preserving continuity with the past. These things have happened before in science. They can happen again. Until then, the parsec remains. Almost no stars sit at this exact distance. The definition is based on arbitrary angle conventions from ancient Babylonian mathematics. It marks no natural boundary in space, yet it appears in virtually every professional astronomy paper written today. It shapes how astronomers think about cosmic distances. It defines the language of stellar distance measurement, all because of a measurement technique from 1838 and the path-dependent processes that made it standard. If someone proposed a completely new distance unit today, would it replace the parsec? Almost certainly not. The existing infrastructure is too substantial. Too many databases use parsecs. Too much software expects parsecs as input. Too many astronomers trained their intuitions around parsecs. The benefits of a new system would need to be dramatic to justify transition costs. This kind of lock-in happens throughout technology and society. Once a standard becomes established, switching costs grow over time. Early on, when few people use a standard, changing is relatively easy. But as more people adopt it, as more infrastructure gets built around it, as more institutions incorporate it into their practices, changing becomes progressively harder. Eventually, you reach a point where switching is effectively impossible even if better alternatives exist. Economists call this path dependence. The path taken to reach the current state determines what states are accessible going forward. You cannot simply jump to the optimal solution if that solution requires abandoning massive investments in existing infrastructure. The costs of transition can exceed the benefits of improvement, even for substantial improvements. The QWERTY keyboard layout represents a famous example. This arrangement of keys was designed in the 1870s for mechanical typewriters. The layout was deliberately inefficient. Keys that are frequently typed in sequence were placed far apart to prevent mechanical jams when typists worked too quickly. This made sense for 19th century mechanical constraints, but became irrelevant once electric typewriters and computer keyboards eliminated the jamming problem. Alternative layouts like Dvorak demonstrably improve typing speed and reduce finger strain. Studies have shown this repeatedly. Yet QWERTY persists as the overwhelming standard. Why? Because billions of people learn to type on QWERTY keyboards. Because computer keyboards come with QWERTY as default. Because touch typing courses teach QWERTY. Because switching would require everyone to retrain, and coordination problems make collective switching nearly impossible, even though everyone might benefit from the change. Railroad gauge, the distance between rails, shows similar path dependence. Standard gauge is 4 feet 8.5 inches. Why this odd number? Because that was the gauge used on early railways in England. And why did early English railways use that gauge? Partly because that was the width of coal mine tramways, which in turn reflected the width of traditional carts, which may have descended from ruts in ancient Roman roads. Nobody chose 4 feet 8.5 inches as optimal through engineering analysis. It emerged from historical contingencies and stuck because once rail networks spread using that gauge, changing became prohibitively expensive. Rolling stock designed for one gauge does not work on another. Switching would require rebuilding entire rail networks simultaneously. The costs are astronomical for benefits that are unclear. The Parsec follows this same pattern. It became standard during the formative period of stellar astronomy. As the field grew, more infrastructure accumulated around this choice. More measurement techniques reported results in parsecs. More databases stored distances in parsecs. More analysis tools expected parsecs as input. More textbooks taught parsecs. More researchers learned to think in parsecs. Each increment of accumulated practice made changing harder. By the mid-20th century, changing would have required coordinated action across a global research community. That coordination is difficult to achieve even when benefits are clear and substantial. For something like distance units, where benefits are modest and uncertain, while costs are definite and concentrated on those doing the changing, coordination becomes nearly impossible. The system locks in. This does not mean the parsec is optimal, or that astronomers believe it is optimal. Many astronomers, if asked, will acknowledge that light years might be more intuitive for general audiences, or that some other unit could have advantages. But acknowledgement of limitations does not create momentum for change. Change requires someone to invest resources in transition with uncertain payoff. Who will volunteer for that task? Research funding agencies want to fund new discoveries, not unit conversions. Universities want to hire faculty who produce research, not faculty who spend time standardizing units. Individual researchers want to publish papers that advance knowledge, not papers explaining unit conversions. The incentive structure does not reward the work required for transitions, even when such transitions might create modest benefits. This reveals something important about scientific progress. It is not just a process of discovering truth and correcting errors. It is also a process of building infrastructure, establishing institutions, training practitioners, and creating shared practices. That infrastructure has enormous value. It enables coordination and accumulation, but it also creates inertia that resists change even when change might be beneficial. Progress in science is not just linear accumulation of knowledge. It also involves periods of stability where existing frameworks and practices solidify. Periods of crisis where anomalies accumulate and frameworks strain, and occasional revolutionary transitions where new frameworks displace old ones. Thomas Kuhn famously described this pattern in his book, The Structure of Scientific Revolutions. Kuhn argued that normal science operates within paradigms, shared frameworks that define what questions are interesting, what methods are legitimate, what counts as explanation. These paradigms are incredibly productive. They focus research effort, they enable accumulation of detailed knowledge, they create sophisticated instruments and techniques, but they also constrain imagination and resist changes that threaten core assumptions. The parsec fits into this picture as a small piece of normal science infrastructure. It is not a paradigm-defining core theoretical commitments. It is a conventional choice about measurement, but it illustrates similar dynamics. Once established, it shapes practice in ways that make alternatives harder to imagine and implement. It is not that scientists are unable to conceive of alternative units. It is that using alternative units would create friction in their daily work, and that friction discourages deviation from standard practice. Standards serve a coordinating function that makes deviation costly, even when alternatives might be individually superior. If you write a paper using light years instead of parsecs, Other astronomers will need to convert your numbers to compare with their work. Your paper becomes slightly harder to use. Reviewers might complain. Editors might require conversion to standard units. These small frictions add up to a strong incentive to conform. This kind of social pressure maintains standards even without explicit rules or enforcement. Nobody will prevent you from using light years in your research. But professional norms and practical considerations nudge everyone toward conformity. The result is a self-reinforcing equilibrium where the standard persists because everyone expects everyone else to use it. Breaking such equilibria typically requires external shock or coordinated collective action. An external shock might be a technological change that makes the old standard obviously inadequate. Coordinated collective action might be an organized effort by professional societies or funding agencies to establish a new standard and create incentives for adoption. Neither has occurred for distance units in astronomy. The parsec persists because it works adequately, and no force has been strong enough to overcome the inertia. What would it take to change? Perhaps a new generation of astronomers who never learned to think in parsecs might push for change. Perhaps integration with other fields using different units might create pressure for harmonization. Perhaps computational tools might advance to the point where unit conversions become trivial, removing practical barriers to using multiple systems. Perhaps some new measurement technique might emerge that makes a different unit more natural. These scenarios are possible, but none seems imminent. More likely, the parsec will simply persist indefinitely. It will remain a peculiar historical artifact, a unit that makes limited intuitive sense but serves its function well enough that replacing it is not worth the effort. Future astronomers will continue learning it during their training, continue using it in their research, and continue explaining it to confused students and interested public audiences. The cycle will continue. This outcome is not failure. It is just reality of how human institutions work. Optimal solutions are often unattainable or not worth the cost of reaching them. Adequate solutions that are already established and widely used tend to persist. This is true for measurement units, true for technology standards, true for organizational structures, true for countless aspects of how humans coordinate their activities. Understanding this helps us have more realistic expectations about change and progress. Change is possible. Standards do shift sometimes, but change requires more than just a better idea. It requires coordination, investment, and often external pressure or crisis. In the absence of those forces, inertia is powerful. Existing systems persist not necessarily because they are best, but because they are established and changing is hard. The parsec story thus becomes a story about path dependence, institutional inertia, coordination problems, and the social construction of scientific practice. These are not romantic topics. They do not involve brilliant insights or heroic discoveries. They involve mundane processes of standardization, training, and infrastructure building. But these mundane processes are what make science work as a collective enterprise. They deserve our attention and understanding. Now let us think about how the parsec connects to deeper questions about the nature of measurement itself. What are we doing when we measure something? At first glance, measurement seems straightforward. We are determining the value of some property, like length, mass, or time. We compare the property to a standard unit and report how many units it equals. Simple, but dig deeper and complications emerge. What makes something a valid standard? How do we ensure different people using the same standard get the same results? How do we deal with measurement uncertainty? How do we extend measurements beyond direct comparison to distances we cannot physically reach or times we cannot directly observe? These questions have deep implications for how science works. The history of measurement shows a gradual progression toward more precise and universal standards. Ancient measurements were often based on human body parts. A cubit was the length of a forearm. A foot was, well, a foot. A yard was supposedly the distance from the king's nose to his outstretched fingertip. These standards were practical for everyday use, but varied between people and regions. Trade and construction required better standardization. Societies began creating physical standards, official measuring rods or weights kept in central locations. If there was a dispute about the length of some sold cloth, you could refer to the official standard rod. This improved consistency within a region, but different regions still had different standards. A foot in one kingdom might differ from a foot in another. This created problems for trade, science, and engineering. The scientific revolution of the 17th and 18th centuries created pressure for universal standards that would be the same everywhere and could be reconstructed if the physical standard was lost or damaged. Natural constants seemed like good foundations. Define units based on properties of nature that are the same everywhere, rather than arbitrary human conventions. The meter was an early attempt at this. Instead of defining it as some arbitrary length, define it as 1/10,000,000th of the distance from the equator to the North Pole. This seems to ground the meter in natural geography. If the standard meter bar was destroyed, you could in principle remeasure the Earth and recreate the meter. This felt more fundamental than basing it on a king's body parts. Of course, this was still somewhat arbitrary. Why 10 million? Why not 5 million or 20 million? Why the distance from equator to pole rather than the circumference of the Earth? These choices were conventions made for convenience by French scientists during the revolutionary period. But the principle seemed sound. Ground measurement in nature, not in human artifacts. Over time, standards evolved toward even more fundamental natural constants. Today, the meter is defined by the speed of light. Specifically, a meter is the distance light travels in vacuum in 1/299,792,458th of a second. This seems beautifully fundamental. The speed of light is a constant of nature, the same everywhere in the universe, as far as we know. If all human civilization were destroyed and aliens found our records, they could reproduce the meter by measuring the speed of light. Except, of course, they would need to know what a second is. The second is defined by atomic transitions in cesium atoms. Specifically, a second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of cesium-133. This is even more fundamental than astronomical measurements, since atomic properties are truly constants of nature. So modern measurement standards are grounded in fundamental physics. They reference properties of elementary particles and fundamental constants like the speed of light. This makes them as universal and reproducible as we can achieve. Any sufficiently advanced civilization should be able to reproduce our standards from the definitions, even without physical artifacts. But notice something interesting. We still need to count something. 9 billion periods of radiation, 299 million fractions of a second. These numbers are arbitrary human choices about how to divide up natural phenomena. Nature does not come pre-divided into seconds and meters. We impose those divisions based on convenience and historical continuity with earlier standards. The parsec sits awkwardly in this progression toward fundamental standards. It is not based on arbitrary human body parts, but it is not based on fundamental physical constants either. It is based on angular measurement conventions from ancient Babylonian mathematics. 1 arcsecond is 1/3600th of a degree, and 360 degrees in a circle is a human convention, not a natural constant. You could argue that the radian is a more natural angular unit. A radian is defined as the angle subtended by an arc equal in length to the radius. There are 2 pi radians in a full circle, and pi is a fundamental mathematical constant that appears throughout nature. Defining angles in radians connects to natural geometry rather than arbitrary divisions. If angles were measured in radians instead of degrees, the parsec would need to be redefined. It would be the distance at which Earth's orbital diameter subtends an angle of 1/3600 times 2 pi radians. That is about 31,416 times smaller angle than 1 radian. This number is less natural than 1 arcsecond, which is at least a clean division of conventional degrees. So the parsec actually becomes less elegant if you try to ground it in more fundamental angular measurements. It works best when you accept conventional degrees and arcseconds as given. This shows how measurement systems can be self-consistent and functional, even when not optimally grounded in fundamental physics. The parsec is internally coherent within a system that uses degrees and arcseconds. It just does not connect as directly to fundamental constants as modern physicists might prefer. Does this matter? For most astronomical purposes, not really. Distances in parsecs work fine for calculations, regardless of whether the definition references fundamental constants. The physics does not care about our choice of units. But from a philosophical perspective about what makes good scientific measurements, the parsec represents an interesting intermediate case between arbitrary convention and fundamental natural standard. This brings us to deeper questions about scientific realism and the relationship between our measurements and actual properties of nature. When we say a star is 10 parsecs away, what exactly are we claiming? We are claiming something about the actual spatial separation between us and that star. But we are expressing that claim using units that are human conventions. The same spatial separation could equally be expressed as 32.6 light years, or 308 trillion kilometers, or any number of other units. None of these expressions is more true than the others. They all describe the same physical reality using different conventional units. The reality is the spatial separation. The units are our tools for expressing and manipulating information about that reality. This seems like a clean distinction. Reality is one thing, our descriptions are another, and we should not confuse the two. But measurement is not quite that simple. We never have direct access to the bare spatial separation. We always access it through some measurement procedure using some instrument operating on some physical principle. Different measurement procedures can give slightly different results due to systematic errors, calibration issues, or fundamental limits of the technique. Which result is the true distance? For nearby stars measured by parallax, different telescopes and analysis methods yield slightly different parallax values. These differences are usually small within the measurement uncertainties, but they mean that distance is not simply a number we read off from nature. It is a value we infer from observations using theoretical models of how the measurement process works, after correcting for numerous systematic effects and sources of error. This becomes even more complicated for distances beyond the reach of parallax. For distant galaxies, we might use several different distance indicators, standard candles, or ruler techniques, each with their own systematics and assumptions. These different methods do not always agree precisely. Astronomers speak of a distance ladder, a series of methods that build on each other, each extending to larger scales, but each introducing additional uncertainties. At the largest cosmic scales, The question of what distance even means becomes conceptually subtle. In an expanding universe, the distance between us and a remote galaxy changes over time as space expands. Do we mean the distance when light left that galaxy, the distance now, the distance when the light reaches us? These are all different values, and which one you want depends on what question you are asking. Cosmologists often use redshift as a distance proxy for exactly this reason. Redshift measures how much light has been stretched by cosmic expansion. It is an observable that connects directly to measurement without requiring a choice about which notion of distance you mean. Different distance definitions can all be calculated from redshift using appropriate formulas, but the redshift itself is more fundamental than any particular distance measure in an expanding universe. This might seem like a digression from the parsec, but it illustrates an important point. Measurement in science is not simple reading of pre-existing values. It is a complex process involving instruments, theoretical models, correction procedures, and interpretive choices. The units we use to express results are part of this apparatus. They are not arbitrary, but neither are they simply discovered in nature. They are constructed by communities of practitioners to serve particular purposes. The parsec is part of that constructed apparatus. It emerged from the practical needs of parallax measurements. It became standard through social coordination. It persists due to institutional inertia. Understanding this does not undermine the reality of stellar distances. The stars really are at definite distances from us, independent of human choices about units. But our knowledge of those distances is mediated through complex practices that involve both technical and social elements. This perspective, sometimes called social constructivism, emphasizes that scientific knowledge is socially constructed while remaining grounded in natural reality. The distances are real. The measurements respond to real properties of nature, but the frameworks we use to interpret measurements, the standards we adopt for expressing results, the units we choose for calculation, all reflect human decisions made in particular historical contexts for particular practical purposes. This is not a contradiction or a problem. It is just how science works. Science is done by humans, and humans operate within social structures with histories and conventions. Those structures shape scientific practice in fundamental ways while not undermining the empirical grounding of scientific claims. We can hold both thoughts simultaneously. The distances to stars are real physical facts, and the parsec is a human convention for expressing those facts. Now let us return to the specific question that might still be puzzling some listeners. Why is the parsec longer than a light year? Both units measure cosmic distances. Both are vastly larger than anything in everyday experience. But one parsec equals about 3.26 light years. Where does this particular ratio come from? The answer lies in the geometry of Earth's orbit and the definition of the parsec. Earth orbits the Sun at an average distance of about 1 astronomical unit. The full diameter of the orbit is therefore 2 astronomical units. When we measure stellar parallax, we are effectively using this diameter as our baseline for triangulation. Observe a star from opposite sides of Earth's orbit, and you are viewing from positions separated by 2 astronomical units. Now imagine a star at a distance of 1 parsec. By definition, that star shows a parallax of 1 arcsecond. This means that when viewed from opposite sides of Earth's orbit, the star appears to shift by 1 arcsecond against background stars. Draw a triangle. The base has length 2 astronomical units. The angle at the star vertex equals 1 arcsecond. Basic trigonometry tells us the distance to the star. For small angles measured in radians, the distance equals baseline divided by angle. 1 arcsecond equals about 1/206,265th of a radian. So distance in astronomical units equals 2 divided by that small number, which gives about 206,000 astronomical units. That is 1 parsec by definition. Convert to kilometers and you get about 30.9 trillion kilometers. Light travels at about 300,000 kilometers per second. How long does it take light to cover 30.9 trillion kilometers? Divide the distance by the speed of light and you get about 9.7 trillion seconds. Divide by the number of seconds in a year, about 31.6 million, and you get about 3.26 years. So 1 parsec equals about 3.26 light years. The ratio emerges from the geometric relationship between Earth's orbital size, the definition of the arcsecond, and the speed of light. Nothing deep or fundamental determines this particular ratio. It is just a consequence of how these different units are defined. If Earth's orbit were a different size, or if we divided circles differently so that 1 arcsecond corresponded to a different angle, the ratio would be different. This is why the parsec can feel arbitrary compared to the light year. The light year connects distance directly to a fundamental constant, the speed of light, combined with a human time unit, the year. That seems fairly natural. The parsec connects distance to angular measurement conventions and the size of Earth's orbit. That seems more contingent on arbitrary choices and accidents of where we happen to live in the solar system. But from another perspective, the parsec is beautifully simple for parallax work. It makes the math trivial. Measure parallax in arcseconds, invert, get distance in parsecs. No need to multiply by strange conversion factors or remember complicated formulas. This is exactly what makes it appealing for working astronomers. The unit that makes the math simplest tends to be the unit that gets adopted and used. Different fields tend to adopt units that simplify their characteristic calculations. Particle physicists use units where the speed of light equals 1, eliminating c from formulas. Chemists use moles to count atoms. Economists use currency units specific to their applications. Each choice trades increased abstraction or unfamiliarity to outsiders for simplicity in the calculations insiders perform most frequently. The parsec makes the same kind of trade. It sacrifices intuitive accessibility for computational convenience. If your job involves measuring parallaxes all day, this trade makes perfect sense. If you are explaining astronomy to the public, the trade seems less favorable. Different stakeholders have different priorities, and those priorities influence which features of a unit seem most important. This is actually a general principle in human practices and institutions. Insiders and outsiders have different perspectives on what matters. Insiders care about features that affect their daily work. Outsiders care about features that affect comprehension and accessibility. There is no objective fact about which perspective is correct. Both are legitimate for their respective purposes. Conflicts arise when decisions must be made about shared standards that affect both groups. In the case of astronomical distance units, insiders won the battle because they control the actual practice of astronomy. Research astronomers decide what units to use in papers, what units to teach to graduate students, what units to implement in analysis software. Public outreach educators might prefer different choices, but they do not control these decisions. So insider priorities dominated, and the parsec became standard. This is not necessarily bad or good. It is just how collective decision-making works when different stakeholders have different priorities and unequal power to shape outcomes. The group doing the work gets to set the standards for that work. People outside the field must either learn those standards or rely on translation and explanation from those within the field. This division is common across specialized occupations. All of this returns us to the fundamental strangeness of the parsec. It is a unit that makes perfect sense from inside astronomy, but seems bizarre from outside. It connects to measurement techniques in elegant ways, but relates to everyday intuitions not at all. It marks no natural boundary, but corresponds to convenient angles. It persists due to institutional inertia, but serves practical purposes well. It is simultaneously arbitrary and functional, contingent and useful, strange and standard. This combination of properties makes the parsec a perfect case study for thinking about scientific standards, social coordination, path dependence, and the human dimensions of scientific practice. It is weird enough to make us question assumptions about how science works, but simple enough to understand without advanced mathematics. It is consequential enough to matter for actual research, but not so fundamental that disagreements about it would threaten core scientific knowledge. The parsec reveals that science is both more human and more social than idealized descriptions suggest. It is not just about making observations and drawing logical conclusions. It is also about coordinating across large communities, establishing conventions, building infrastructure, navigating trade-offs between competing goals, and making pragmatic choices under uncertainty. These social and practical dimensions are not corruptions of pure science. They are necessary features of how science actually functions as a collective human endeavor. Understanding this makes us more sophisticated in how we think about science and scientific claims. We can appreciate that scientific knowledge is both objective and constructed. The facts that science discovers are real features of nature, independent of human opinions. But the frameworks we use to express, organize, and reason about those facts involve human choices and social processes. Both elements are essential. Neither can be eliminated or reduced to the other. The parsec embodies this duality. The distances it measures are real physical separations between us and distant stars. Those separations exist whether or not humans are around to measure them. But the parsec itself, as a unit for expressing those distances, is a human invention reflecting practical needs, historical accidents, and social coordination. We cannot point to the parsec out there in nature. We can only point to the human practices that give it meaning and utility. This is true of scientific concepts generally. They refer to real aspects of nature while also embodying human interpretive choices. Force, energy, species, gene, planet. These are all concepts that pick out real patterns in nature while also reflecting decisions about how to carve up and organize our understanding of nature. The patterns are real. The concepts are human tools for thinking about those patterns. Both levels matter. The parsec story helps us see this clearly, precisely because the unit is so obviously conventional, while the distances it measures are so obviously real. Nobody could seriously doubt that stars are at definite distances from us. But nobody would claim the parsec was somehow discovered rather than invented. This makes it an unusually clear case where the distinction between natural reality and human construction is easy to perceive. More complex scientific concepts blur this distinction. Is species a natural category or human construct? Are planets, dwarf planets, or not planets according to nature, or just according to human definitions? Is time absolute or relative? These questions are harder because natural patterns and human interpretive frameworks are more entangled. The parsec, being a measurement unit, keeps them more cleanly separated. This pedagogical value might be one more reason it is worth understanding the parsec story. Let us consider one more angle on all this. What does the parsec reveal about scientific progress over long timescales? Does the persistence of a 19th century unit indicate that astronomy has stagnated? Or does it indicate that early astronomers made such good choices that their frameworks still serve modern purposes? Or something else entirely? The answer is something else. The parsec persists, not because it is optimal or because astronomy has stagnated, but because the costs of changing exceed the benefits for the current community. This tells us that scientific progress is not just about improving our theories and techniques. It is also about accumulated infrastructure, trained intuitions, and coordination among practitioners. Those elements change much more slowly than knowledge itself. Astronomy has progressed enormously since the 1830s. We have discovered that stars have finite lifetimes. We understand stellar evolution, nuclear fusion in stellar cores, the formation of heavy elements in supernova explosions. We have discovered galaxies, clusters of galaxies, and large-scale cosmic structure. We have measured the expansion of the universe, discovered dark matter and dark energy, detected gravitational waves from merging black holes. The field has been revolutionized multiple times. Yet we still use parsecs. The unit has proven flexible enough to accommodate all of this new knowledge. It scales to different regimes through prefixes like kiloparsecs and megaparsecs. It connects to new distance measurement techniques as they are developed. It serves the needs of modern cosmology as well as it served 19th century stellar astronomy. This is not stagnation. This is a successful, well-designed framework that continues to be useful across changing circumstances. This reveals an important feature of good scientific infrastructure. It should be flexible enough to accommodate growth and change without requiring complete replacement. The parsec achieved this flexibility by being a simple, geometric concept that could scale to different regimes and connect to different measurement techniques. It did not embed strong theoretical assumptions that would become outdated as theories changed. It remained a useful, practical tool even as the theoretical context shifted dramatically. Compare this to certain theoretical concepts that do become outdated and replaced as theories change. The concept of phlogiston in chemistry, representing a supposed fire element released during combustion. The concept of luminiferous ether in physics, representing a supposed medium for light waves. These concepts were central to earlier theories, but could not survive the transition to better theories. They embedded assumptions that turned out to be wrong about the fundamental nature of phenomena. The parsec does not have this problem because it is not a theoretical concept at all. It is a measurement unit, a tool for expressing quantities. Tools can persist across theoretical revolutions if they remain useful for practical purposes. This is why parsecs survive where phlogiston did not. One is infrastructure, the other is theory. Infrastructure has different dynamics of persistence and change than theory does. This suggests a more nuanced picture of scientific progress than simple accumulation of truth or replacement of false theories with true ones. Progress involves many kinds of change operating on different timescales. Theoretical understanding can shift rapidly when new evidence emerges or better frameworks are developed. Measurement techniques evolve more gradually as instruments improve and methods are refined. Infrastructure and standards change very slowly due to coordination problems and switching costs. All of these are happening simultaneously but at different rates. The result is a complex ecology of practice where elements from different historical periods coexist and interact. Modern astronomers use parsecs from the 1830s, spectroscopy from the late 1800s, electronic detectors from the mid-20th century, digital data analysis from recent decades, and theoretical frameworks from various periods spanning centuries. This is not incoherent. It is how complex practices accumulate over time combining elements from different eras into working systems. Understanding this temporal complexity helps us avoid both naive progressivism and cynical relativism. Naive progressivism assumes science simply accumulates truth, and obsolete elements get discarded. This misses how infrastructure and standards can persist for non-epistemic reasons related to coordination and switching costs. Cynical relativism assumes that persistence of non-optimal elements reveals science as arbitrary or irrational. This misses how practical functionality can justify persistence, even when alternatives might be theoretically superior. The reality is more interesting than either extreme. Science is a cumulative and progressive enterprise that builds increasingly accurate understanding of nature. But it is also a practical human activity constrained by coordination problems, path dependence, and institutional inertia. Both dimensions are real and important. Accounting for both gives us more sophisticated understanding of how science actually works and how it changes over time. The Parsec, once again, illustrates this beautifully. It is neither a deep truth about nature nor an arbitrary social convention. It is a practical tool that emerged for good reasons, persists for understandable reasons, and serves useful functions while having recognized limitations. This combination is typical of many elements of scientific practice. They are functional without being optimal, historically contingent without being arbitrary, socially maintained without being purely social constructs. After all this analysis, we can return to the simple question we started with. What is a parsec? It is a unit of distance defined as the distance at which a star shows a parallax of 1 arcsecond when observed from opposite sides of Earth's orbit. It equals about 3.26 light-years, or about 30 trillion kilometers. It is the standard distance unit used in professional astronomy, appearing in virtually every research paper dealing with stellar or galactic distances. It is based on parallax geometry and angular measurement conventions from ancient Babylonian mathematics. But we now understand that this simple definition conceals a rich story about measurement, standards, scientific practice, and human coordination. The parsec is not just a number. It is a window into how science actually works as a social and technical enterprise. It reveals the interplay between natural reality and human construction, between objective measurement and conventional choice, between technical functionality and historical contingency. Every time you encounter an astronomical distance measured in parsecs, you can now see layers of meaning that were invisible before. You see the measurement technique from 1838 that motivated the unit. You see the geometric relationship between angles and distances. You see the social coordination that made this particular unit standard. You see the institutional infrastructure that maintains the standard across generations. You see human choices shaping scientific practice in ways that persist for centuries. This kind of sophisticated understanding makes science more interesting, not less. It shows that science is a profoundly human activity, shaped by our history, our psychology, and our social organization, while remaining grounded in empirical investigation of natural reality. This combination makes science both more impressive and more comprehensible. It is an amazing collective achievement precisely because it is a human achievement, built and maintained by communities of people working together across time and space. The parsec will likely continue to dominate astronomical distance measurement for the foreseeable future. New astronomers will continue learning it, using it, explaining it to students and public audiences. The cycle will continue because changing is hard and the current system works adequately. This is not failure or stagnation, it is just how human institutions function. Established practices persist unless strong forces create pressure for change. Meanwhile, the stars remain at their distances, measured in parsecs or any other unit we choose. The light that left them years or centuries or millennia ago continues traveling through space until it enters our telescopes and strikes our detectors. That light carries information about those distant objects, encoded in its spectrum and intensity. We decode that information using sophisticated instruments and analytical techniques. We express the results in conventional units like parsecs that connect us to centuries of prior work. And through this complex apparatus of measurement and analysis, we gradually build understanding of the cosmos. Let us explore one more dimension of this story. How do astronomers actually measure parallaxes today? And how does this relate to the parsec as a unit? Modern parallax measurements bear little resemblance to what Bessel did in the 1830s, yet the fundamental geometric principle remains the same. Understanding modern techniques reveals both how far the field has progressed and how the parsec continues to serve its original function. Bessel used a heliometer, an instrument with a split objective lens that could measure small angular separations. He observed 61 Cygni repeatedly over many months, comparing its position to nearby reference stars. Each observation required manual positioning of telescope and instrument, careful reading of scales, correction for numerous systematic effects. The entire process was laborious and prone to error. His final parallax measurement had substantial uncertainty. He could only claim that the star was somewhere in the range we now recognize as correct, but the error bars were large. Throughout the late 1800s and early 1900s, parallax measurements gradually improved as instruments and techniques advanced. Photographic plates replaced visual observations, allowing more objective position measurements. Better telescope mountings reduced mechanical errors. Understanding of atmospheric refraction improved, allowing better corrections. Statistical methods for combining multiple observations became more sophisticated. The precision increased from arcseconds to tenths of arcseconds to hundredths of arcseconds. But Earth-based observations hit fundamental limits. Atmospheric turbulence blurs stellar images, limiting how precisely positions can be measured. Even at the best observatory sites, atmospheric seeing is rarely better than 1 arcsecond. This means parallaxes smaller than about 1/10 of an arcsecond become very difficult to measure reliably from ground-based telescopes. That limits parallax distance measurements to stars within about 10 parsecs. This is actually not many stars. Our galaxy contains hundreds of billions of stars, but only a few thousand sit within 10 parsecs of us. To map the structure of the galaxy, to understand stellar populations and distributions, to measure distances to star clusters and associations, astronomers needed techniques that could reach much farther than direct parallax. Several methods emerged during the 20th century for measuring distances beyond the parallax limit. Each method had its own assumptions, systematics, and uncertainties. Each extended the distance ladder one more step, allowing measurements to progressively larger scales. Understanding this ladder helps explain why the parsec remains useful, even though most astronomical distances cannot be measured by parallax anymore. The first step beyond parallax uses stellar motions. Stars move through space at typical velocities of tens of kilometers per second. This motion has two components. The radial velocity, motion toward or away from us, can be measured from Doppler shifts in spectral lines. The tangential velocity, motion perpendicular to our line of sight, causes the star to drift slowly across the sky over years and decades. This drift is called proper motion. If you can measure both radial velocity and proper motion, you can determine the star's total velocity through space. But proper motion is an angular rate, typically measured in milliarc seconds per year. To convert this angular rate into actual velocity in kilometers per second, you need to know the distance. More distant stars show smaller proper motions for the same physical velocity. So you cannot directly determine distance from proper motion alone. However, if you observe a group of stars that are all at the same distance, like a star cluster, you can use a clever statistical technique called moving cluster parallax. The stars in a cluster all form together and are moving together through space with approximately the same velocity. Their proper motions on the sky will all point toward a single convergent point, the direction the cluster is moving. By analysing the pattern of proper motions geometrically, you can determine the cluster's distance without needing individual parallaxes. This technique works beautifully for nearby open clusters like the Hyades, which sits about 45 parsecs away. Parallax can measure distances to the brightest individual stars in the Hyades, but moving cluster analysis gives an independent distance determination for the whole cluster. The two methods agree, which validates the technique. Then moving cluster analysis can be applied to more distant clusters where individual parallaxes are too small to measure. Another powerful technique uses main sequence fitting. Stars spend most of their lives burning hydrogen in their cores, during which they sit on the main sequence in diagrams plotting luminosity against temperature. The main sequence has a well-defined relationship between colour and absolute brightness. If you can measure the apparent brightness and colour of main sequence stars in a cluster, you can determine how far away they must be to produce the observed apparent brightness. This is main sequence fitting. The challenge is calibrating the relationship between colour and absolute brightness. You need reference stars with known distances to establish the calibration. This is where parsecs and parallax measurements become crucial. Nearby stars with measured parallaxes provide the reference points that calibrate the main sequence. Without those parallax measurements, the whole technique would lack foundation. The parsec distances measured by parallax anchor the entire distance scale for more remote objects. Variable stars provide another powerful distance indicator. Certain types of stars pulsate regularly, swelling and shrinking in cycles that produce regular variations in brightness. Cepheid variables, named after delta Cephei, which shows this behaviour, follow a remarkable relationship discovered by Henrietta Leavitt in the early 1900s. The period of pulsation correlates directly with intrinsic luminosity. Longer period Cepheids are intrinsically brighter. This period luminosity relationship makes Cepheids incredibly useful as standard candles. Observe a Cepheid, measure its pulsation period, and you immediately know its intrinsic luminosity. Compare that to its observed apparent brightness, and you can calculate distance. Cepheids are bright enough to be observed in distant galaxies, allowing distance measurements out to tens of megaparsecs. Edwin Hubble used Cepheids in the 1920s to prove that spiral nebulae are actually separate galaxies far beyond the Milky Way. But here is the crucial point. The period luminosity relationship must be calibrated. You need to observe Cepheids with known distances to establish how period relates to absolute luminosity. Those calibration distances come from parallax measurements for nearby Cepheids and from main sequence fitting for Cepheids in clusters whose distances are known from parallax-based methods. Once again, the parallax measurements in parsecs provide the foundation. The entire cosmic distance scale builds on that foundation established in the 1830s. For the most distant objects, in galaxies hundreds or thousands of megaparsecs away, even Cepheids become too faint to observe. Astronomers use type Ia supernovae as standard candles at these scales. These stellar explosions reach intrinsic brightnesses so extreme they can be seen across billions of light years. They show remarkably consistent peak brightnesses, making them useful as standard candles. With appropriate corrections, type Ia supernovae allow distance measurements across much of the observable universe. These distance measurements revealed one of the most profound discoveries in the history of cosmology. In the 1920s, Edwin Hubble found that distant galaxies are receding from us, with recession velocities proportional to distance. The universe is expanding. This discovery transformed our understanding of cosmology and eventually led to the Big Bang theory. Without reliable distance measurements, this discovery would have been impossible. And those distance measurements ultimately trace back to parallax measurements of nearby stars expressed in parsecs. This illustrates something profound about scientific knowledge. It forms an interconnected web where pieces support and validate each other. Parallax measurements validate moving cluster analysis. Moving cluster analysis calibrates main sequence fitting. Main sequence fitting calibrates the Cepheid period luminosity relationship. Cepheids calibrate type Ia supernovae. Type Ia supernovae reveal cosmic expansion. Each step builds on previous steps. The entire structure depends on foundations established over a century ago. The parsec sits at the base of this structure. It is the natural unit for expressing parallax distances, and those parallax distances anchor everything else. This gives the parsec a special status, not just as a convenient unit, but as the foundational distance unit for the entire cosmic distance ladder. Changing to a different unit would require recalibrating everything downstream. This is another source of inertia keeping the parsec standard. Modern space-based missions have revolutionized parallax measurements by escaping Earth's atmosphere. The Hipparcos satellite, launched in the 1980s, measured positions and parallaxes for about 100,000 stars with precision down to milliarc seconds. This extended reliable parallax distances from about 10 parsecs to about 100 parsecs, increasing the volume of space mapped by a factor of 1,000. More recently, the Gaia mission has taken this much further. Launched in 2013, Gaia continuously scans the sky, measuring stellar positions with unprecedented precision. For bright nearby stars, Gaia achieves precision down to 10 micro-arcseconds. A micro-arcsecond is 1/1,000,000th of an arcsecond. This incredible precision extends parallax distance measurements out to distances of several kiloparsecs, truly mapping the structure of our entire galactic neighborhood. Gaia has measured parallaxes for more than 1.7 billion stars. Think about that number, 1.7 billion individual distance measurements. This is revolutionary for astronomy. We can now create three-dimensional maps of the Milky Way, trace the motions of stellar streams, identify distinct stellar populations, study the distribution of interstellar dust, all based on individual parallax measurements for 1 billion stars. Every single one of those measurements is reported in milliarc seconds of parallax, directly convertible to distances in parsecs. The entire Gaia catalog uses these units. Analysis software expects these units. Research papers analyzing Gaia data use these units. The parsec is more thoroughly entrenched now than ever before, precisely because it is the natural unit for the kind of measurements Gaia performs. This demonstrates how advancing technology can actually strengthen existing standards rather than replacing them. Gaia made parallax measurements vastly more powerful and extensive, but it did not change the fundamental geometric relationship between parallax angles and distances. If anything, having billions of high-precision parallax measurements makes the parsec even more valuable as the standard unit. Converting all those measurements to light years would serve no purpose while creating substantial inconvenience. Future missions will push even further. Proposed space telescopes could achieve micro-arc-second precision for fainter and more distant stars, extending parallax measurements across the entire galaxy. Ground-based telescopes using adaptive optics and interferometry continue improving their precision as well. The next generation of extremely large telescopes, with mirrors 30 to 40 meters in diameter, will achieve angular resolutions rivaling space telescopes for bright objects. Parallax measurements will continue advancing, and those measurements will continue being expressed in milliarc seconds and converted to parsecs. This look at modern techniques reveals that parallax measurement has evolved from a difficult individual achievement in the 1830s to a routine automated process measuring billions of distances. But the geometric principle remains identical. The unit that Bessel effectively established in 1838 still serves today. This is remarkable continuity across nearly 2 centuries of dramatic technological and scientific advancement. One fascinating aspect of the Parsec story involves how astronomers think about and visualize cosmic distances. Professional astronomers develop intuitions calibrated in parsecs. When someone says a star cluster is 500 parsecs away, an experienced astronomer immediately has a sense of scale. That is nearby on galactic scales, but far enough that individual parallaxes are challenging to measure. That is the distance where you might use main sequence fitting or star counts to determine distance. That is close enough that interstellar extinction might not be too severe, but far enough that you need to correct for it carefully. These intuitions are crucial for doing research efficiently. They guide quick estimates and sanity checks. They help identify probable errors in data. They shape how astronomers think about spatial relationships in the galaxy. And they are all calibrated in parsecs because that is the unit used throughout their training and career. Asking astronomers to switch to light years would not just require mathematical conversions, it would require rebuilding intuitions developed over years of practice. This human dimension of measurement units is easy to overlook, but fundamentally important. Units are not just mathematical conversion factors, they are cognitive tools that shape how we think about quantities. Familiar units feel natural and support intuitive reasoning. Unfamiliar units feel awkward and require conscious conversion that interrupts thought. This is why professionals resist changing units, even when alternatives might have technical advantages. The cognitive cost of retraining intuition is substantial. Consider how Americans think about temperature. Fahrenheit feels natural because we grew up with it. 0 degrees is cold, 50 is cool, 70 is comfortable, 90 is hot, 100 is very hot. These numbers connect to bodily experience and memory. Celsius does not feel natural to most Americans, even though it is objectively a better scale with more logical reference points. 0 for freezing, 100 for boiling. Clean decimal relationships. But the technical advantages do not overcome the cognitive disadvantage of unfamiliarity. The parsec situation is similar. Astronomers grow up professionally with parsecs. They develop rich networks of associations and intuitions calibrated in that unit. Light years, or any other unit, would require rebuilding those networks. The effort involved is not trivial. For working scientists, this cognitive switching cost can outweigh seemingly clear technical advantages of alternative units. This reveals another dimension of why standards persist. Beyond institutional infrastructure and coordination problems, there are genuine cognitive and psychological barriers to change. People are not computers that can instantly switch between equivalent representations. We think through familiar frameworks and categories. Changing those frameworks requires mental effort and temporary reduction in effectiveness while new intuitions develop. People rationally resist that cost unless benefits are compelling. All of this brings us full circle to the question of whether the parsec is good or bad, right or wrong. These are the wrong questions. The parsec is not good or bad in any absolute sense. It is a human tool that serves particular purposes for particular communities. It works well for those purposes within those communities. It is less suitable for other purposes or other audiences. This is normal for specialized tools. A better question might be, given that the parsec exists and is entrenched, what should different stakeholders do? Professional astronomers should probably keep using parsecs for technical work where they provide genuine advantages. They might explain their reasoning better to help outsiders understand why the choice makes sense for insiders. Science educators should probably teach both parsecs and light years, explaining the different contexts where each is useful and the reasons for the professional preference for parsecs. They should not pretend that light years are somehow more fundamental or that parsecs are just confusing jargon. Science communicators writing for general audiences should probably use light years when communicating with non-specialists, since that is more accessible, but they might briefly explain that professional papers use parsecs and why to give readers insight into how science actually works. This builds scientific literacy beyond just communicating facts. It helps people understand the practice and culture of science. Policymakers and funders should recognize that scientific standards and practices serve important functions even when they seem opaque to outsiders. They should be cautious about mandating changes without deep understanding of how current systems actually work and why they persist. Well-intentioned reforms can create more problems than they solve if they disrupt functioning coordination mechanisms. Each stakeholder group has legitimate interests and perspectives. The challenge is coordinating across these groups when their interests do not perfectly align. The Parsec survived this coordination challenge because astronomers had enough autonomy to choose their own standards for their own work. In other contexts where different groups have more equal power to shape standards, negotiations can be more contentious and outcomes more uncertain. This is fundamentally a political process, not just a technical one. Politics is not a dirty word here. It just means negotiating between different groups with different interests and values to reach collective decisions. Science is not apolitical just because it is empirical. Scientists must negotiate standards, allocate resources, establish priorities, manage institutions. All of this involves politics in the sense of collective decision-making under conditions of partial disagreement and competing interests. The Parsec emerged from this political process with astronomers as the primary stakeholders. They chose a standard that served their needs. That standard persists because they continue to find it useful and because changing would impose costs. This is a reasonable, functional outcome, even if it creates communication barriers with non-specialists. As long as those communication barriers do not severely impede the public understanding or support of astronomy, the situation seems acceptable. One could imagine scenarios where the communication barrier becomes more problematic. If astronomical distances were frequently relevant to public policy decisions, the gap between professional units and public intuition could create real problems. But astronomical distances are not typically policy relevant, except in very specialized contexts like planetary defense against asteroid impacts. For most purposes, the public does not need to think much about parsecs or stellar distances at all, so the communication gap is tolerable. This pragmatic perspective helps us avoid unnecessary anguish about standards and conventions. Not every technical choice needs to be optimized for all possible purposes and audiences. Specialized communities can use specialized tools as long as they can translate when needed for wider communication. Complete standardization across all contexts is neither necessary nor always desirable. Different tools for different jobs make sense. The Parsec story ultimately reveals something about how human coordination works at scale. We create standards and conventions to enable cooperation. We invest in infrastructure built around those standards. We train people to use those standards effectively. Once established, standards become self-reinforcing through network effects and switching costs. This creates both stability and inflexibility. Standards persist beyond their original context because changing is hard. This is neither good nor bad in itself. It is just how social coordination works. Understanding these dynamics makes us more sophisticated about science and about human institutions generally. We can recognize that much of what seems natural or inevitable is actually contingent and constructed. Alternative arrangements could have worked. Different choices might have produced different outcomes. Yet the arrangements we have are not arbitrary either. They emerge from real needs and constraints. They serve genuine functions. They reflect intelligent responses to practical problems, even when those responses are not globally optimal. The Parsec embodies this pattern. It was a clever solution to a practical problem in Parallax work. It became standard through social coordination. It persists due to institutional inertia and network effects. It continues to serve useful functions while having recognized limitations. This makes it typical rather than exceptional. Most elements of human practice have similar profiles, combining intelligent design with historical accident, functionality with arbitrariness, conscious choice with unintended path dependence. Recognizing this pattern helps us be more realistic about possibilities for change and improvement. Change is possible, but requires more than just having better ideas. It requires coordinating action across many individuals and institutions. It requires overcoming switching costs and path dependencies. It requires building new infrastructure and retraining people. These are social and organizational challenges as much as technical ones. Sometimes the effort is worthwhile. Sometimes existing arrangements are good enough that change is not worth the cost. Wisdom lies in discerning which situation you are in. For the Parsec, the professional astronomy community has implicitly decided that existing arrangements are good enough. This seems reasonable given the functions the unit serves, the infrastructure built around it, and the modest benefits alternative units would provide. Perhaps someday circumstances will change enough to shift this calculus. Perhaps some technological or conceptual revolution will make parsecs obsolete in ways currently hard to imagine. Until then, the parsec endures as a testament to choices made nearly 2 centuries ago and the path-dependent processes that locked those choices in. This long exploration of a simple distance unit might seem excessive to some readers. Why spend so much time on what is ultimately just a unit conversion factor between different ways of measuring the same thing? The answer is that careful examination of seemingly small technical details can reveal deep patterns about how science works. The parsec is not important in itself. Almost any other element of scientific practice could serve equally well as a case study. But precisely because the parsec is relatively simple and self-contained, it makes an excellent vehicle for exploring larger issues. Those larger issues include the nature of measurement, the role of conventions in science, the processes of standardization and coordination, the dynamics of path dependence and lock-in, the tensions between insider and outsider perspectives, the interplay of technical and social factors in shaping practice. These issues appear throughout science and beyond. Understanding them helps us understand how human knowledge and institutions develop and change over time. The parsec gives us a concrete anchor for abstract discussions about these topics. Rather than talking vaguely about scientific conventions or measurement theory, we can point to a specific example and trace its history and implications in detail. This grounds the discussion and makes it easier to see what is at stake. Abstraction is valuable for identifying general patterns, but concrete examples are valuable for making those patterns real and comprehensible. Moreover, the parsec is genuinely weird and interesting in its own right. It is not an artificial example constructed for pedagogical purposes. It is a real unit used daily by thousands of astronomers worldwide. It shapes how research gets done and communicated. It connects to fundamental questions about how we know the distances to astronomical objects. Yet almost nobody outside professional astronomy knows what it is or understands why it exists. This combination of importance within a field and invisibility outside that field makes it fascinating. The parsec reminds us that behind every measurement, every calculation, every scientific claim, there are humans making choices about methods, units, standards, and conventions. Those choices matter. They shape what questions can be asked easily and what questions become awkward. They determine what calculations are simple and what require tedious conversions. They influence how practitioners think about the domain and what intuitions they develop. Understanding these human dimensions of science makes us better equipped to evaluate scientific claims, understand scientific debates, and appreciate the actual practices that produce scientific knowledge. This understanding is valuable for anyone trying to be scientifically literate in the modern world. Science is not a black box that produces certified truths. It is a complex human endeavor with its own culture, practices, and institutions. Those elements are not corruptions or obstacles to pure truth-seeking. They are necessary features of how collective knowledge production actually works. Acknowledging this does not undermine science. It shows the remarkable achievement that science represents, humans coordinating across generations and cultures to accumulate reliable knowledge about nature despite all the practical and social challenges involved. The parsec, in the end, is a small part of that larger achievement. It is one standard unit among many that enable astronomical research. It works well enough to persist across nearly 2 centuries. It will likely continue working well enough to persist for many more decades or centuries. And through all that time, astronomers will continue measuring distances, expressing them in parsecs, and gradually building deeper understanding of the cosmos. The choice of units matters for practice, but not for the reality being measured. The stars remain at their distances, regardless of how we label them. This is science in action, not pristine logical deduction from first principles, not pure observation uncorrupted by human choice, but careful empirical investigation mediated through instruments and interpretive frameworks that are both technically powerful and historically contingent. Both aspects matter. The technical power lets us discover genuine patterns in nature. The historical contingency reminds us that we are doing this work using tools we have built for purposes we have defined, according to conventions we have established. Thank you for spending these hours exploring the strange story of the parsec. If this changed how you think about scientific standards, about how science actually works as a human endeavor, about the ways history and social factors shape current practice, then the time was well spent. Keep looking up at those stars scattered across the night sky. They are not going anywhere, at least not on human timescales. And whether we measure their distances in parsecs, light years, astronomical units, kilometers, or some future unit we have not invented yet, their light has traveled across the cosmos to reach us. That remains profound and worthy of wonder, no matter what units we choose to describe it. Good night.